And now I'm happy to introduce our speaker today, Ben Raichel from UT Dallas. And so Ben has got his doctorate with Sariel Har-Peled from Urbana-Champaign. And he has been at UT Dallas for a while, and he's works on various algorithmic problems with lots of work in computational geometry, and today would be one of those examples, and I will let him speak rather than take up the time. Please go ahead.
Okay, so thank you, Boris. So yeah, I'm Benjamin Raichel. This is The Road to the Closest Point is Paved by Good Neighbors. It's joint work with Sariel Har-Peled and Eliot Robson, and I'm happy to announce that this paper was just recently accepted to SOSA 2026. So I'll be presenting it there in January, but you get the full version. Okay, so let's see. There we go. Sorry, 1 second. Let me just adjust some things on my side. Okay, good. So today we're going to talk about the nearest neighbor problem. So what's that? I give you a set P of endpoints from a metric space. So here X is my ground set and D is my distance function. And I want to find the nearest neighbor, N, in this point set P to a given query point Q, right? So if this is, say, my point set in the plane, then given this red query point, I want to find the nearest neighbor in my point set. And in this case, it's this blue point, right? So you can state this in general metric spaces, but really here we're going to focus on the Euclidean case. So X here is, d-dimensional Euclidean space with the Euclidean metric, although these results immediately apply to metrics of doubling dimension D. So you can ask, why would you study this problem? There's lots of reasons. In the plane, there's a very natural motivation. I have a bunch of cell phone towers. I take out my cell phone. I want to connect to the nearest tower. That's a nearest neighbor query. In high dimensions, this has direct applications for machine learning for classification, right? Because if these points represent, say, images that I've seen in the past, these are high dimensional points, images, and then for each one, let's say I already know its label, right? So this image is a cat, this image is an airplane, and then a new image comes in that's not labeled, and I want to assign it a label. A natural thing to do is to say, well, I'll assign it the label of the nearest neighbor. Okay. So obviously they do things more complicated than this, but this basic idea is useful in machine learning. Okay, so we want to be able to compute the nearest neighbor. So obviously I can do this in linear time, trivially. I just scan all of the points and I just return the exact nearest neighbor, right? So that's not interesting. The question is, can we pre-process the point set so that I can answer these queries faster, right? So this naturally leads us to the Voronoi diagram, right? So the Voronoi diagram is a partition of space into cells, each consisting of all the points whose nearest neighbor is a given point from my input set, right? So if I look here at this green cell is the set of points in the plane that call this black point their closest point. Okay, so that's the Voronoi diagram. And indeed, in the plane, the Voronoi diagram is very nice, right? It has linear size. It can be computed in near linear time, along with a point location data structure that'll tell you which cell you're in, such that you can answer queries in logarithmic time. So this is really ideal in the plane, right? So I have small size, small query time, small pre-processing, right? So those are typically the three quantities that we look at: time for the query, storage size, and maybe slightly to a lesser extent, the pre-processing time. Okay. Now, the issue is that in high dimensions, the Voronoi diagram's complexity explodes, right? So the complexity is n to the d over 2. Now, you can get a data structure which kind of matches this, right? Clarkson showed that you can get logarithmic query time with this d to a constant factor, and you can do it with n to the O of d space. But, for even moderate values of d, this is just too expensive, right? The storage space is just too large. Maybe I'll accept some constant to a d, but n to the d is too much. And even worse, assuming the strong exponential time hypothesis, you can argue that getting, polynomial time in both n and d with sublinear query time is just not going to happen. Okay? So, but this is all for exact computation. What about approximation, right? This naturally suggests we should move towards approximation, at least for, dimensions higher than the plane. So what's the approximate nearest neighbor problem? I give you a point set P again, a query Q, and now let T be the true nearest neighbor. Okay, so throughout the talk, T will denote true nearest neighbor for Q. And I want you to return a point, which is not necessarily the nearest neighbor, but is at least a 1 plus epsilon approximate nearest neighbor. That is, the distance from Q and P is at most 1 plus epsilon Q to T, right? So in this figure, if I just expand that ball by a factor of 1 plus epsilon, as long as P is within that expansion, then it's a 1 plus epsilon neighbor. It's not necessarily next to T, but it's within that expanded ball, right? And then epsilon is some parameter which you set, which is your sort of tolerance for error. Okay, so there's a lot of prior work on this. I'm not going to go into all the results. I'll just give you a couple results. So for constant dimensions, KD tree-based approach can give you sort of near linear preprocessing, linear space, and logarithmic query time. But here that C, that constant, is dependent exponentially on the dimension, as we expect, right? D over epsilon to the D. So you might say, okay, for high dimensions, can I do something which isn't exponential in the dimension? And so for higher dimensions, there is something called LSH, so locality sensitive hashing, which gives this kind of more scary looking space and query time. But you just look at these terms in the middle here, n to the 1 plus 1 over 1 plus epsilon squared space, and n to the 1 over 1 plus epsilon squared preprocessing, which you should read that as I'm getting subquadratic space and I'm getting sublinear query time. Okay. And sort of from a theory side, these results are at least near optimal in some sense, although there's a lot of other algorithms with sort of different trade-offs in this preprocessing space and query time. Okay. But actually, my focus today is not on the theoretically best algorithm. Instead, what I want to do is talk about a particular strategy to get nearest neighbors or approximate nearest neighbors that's used in practice. Okay, so it's a very simple idea at a high level, modulo all the details, of course. But the idea is the following. I'm going to build a sparse directed graph over my point set. So obviously this is sort of the key how I build this graph, but let's say I have this sparse directed graph over my point set P. Then given a query point Q, I'll just start at some point in this graph and I'll repeatedly move closer to the query in the graph, right? And then there's sort of two natural ways you could do this. You could keep a queue of sort of the part of the graph that you've seen so far, and then, pick the best thing from the queue. This is kind of more like a Dijkstra style search, but I might want to bound the length of this queue to keep the cost down. Or I can be even simpler here. I can just be completely greedy. So if I'm at a vertex, I just check, do I have a neighbor which is closer? If I do, I move to it. And then even there's two versions of greedy, right? You can say, I'll move to my best neighbor, which would require scanning all of your neighbors. Or you can just say, the first time I see a neighbor, I'll jump to it if it's closer, right? So sort of two greedy versions, an impulsive one and a more careful one. So let me just show you on a figure what this looks like. So here, this red point is my query. And let's say I start in my graph at this blue and yellow point, right? So then I check, do I have a neighbor which is closer? Indeed, I do. So I move to that neighbor. Again, do I have a neighbor which is closer? I do. So I move to that. Now you can already see here there were two choices, right? I could have picked either neighbor. I picked this one. This is actually a worse neighbor in terms of it being further from the query than this other choice. But here I'm doing this impulsive, greedy thing. Okay. And again, I repeat, I go somewhere closer if I have a neighbor that's closer. And again, I go somewhere closer. I reach this teal point, and now I'm stuck, right? Anywhere I go locally, I'm further away. So this is my approximate nearest neighbor. It's not the nearest neighbor, In fact, the nearest neighbor is this point up and to the right from the road one. And had I gone, up and down on the previous step, I would have actually reached it. But that's okay. I got close, right? So this is the hope that we can build some sort of sparse graph such that we run this trivial algorithm on the sparse graph and get a good approximate nearest neighbor. Okay. So if the idea is to build graphs for nearest neighbor, this actually does have a long history. Back in the 90s, we have some papers getting n over epsilon to the d minus 1 log n space and log cubed n over epsilon to the d minus 1 query. So this is, not exactly matching those optimal results from a few slides ago, but it's doing quite well. Um, and then Clarkson gave a result where I put a 1/2 in that exponent. So I'm kind of taking a square root of that epsilon term. And now I have a log spread instead of log n. And over here, I also get that square root. And then I have log spread log n instead of log cubed. So if you're not familiar with the spread is the ratio of the maximum distance in the point set divided by the minimum distance. So you can kind of think of this as the scale of the point set. Okay. Now, in theory, log spread may be large. Okay, so on the theory side, there's a fair amount of papers which try to remove these log spread factors, but in practice, it's small. Okay, or often, not always, but often is small. Even for some of these high-dimensional data sets, even the spread itself, not just the log of the spread, but the spread itself might be small. So we're going to be okay with log spread terms in this talk. We're just going to view those as kind of log n's. Okay. Good. So as I said, this graph-based approach, there's a whole sequence of papers which produce these sparse graphs and then run, some simple procedure over them for the query. And they give good empirical performance, but they don't come with approximation guarantees, right? So as good theoreticians do, people try to um, bring theoretical guarantees to this. So first, let me say that disk ANN, which is the one we're going to talk about right now. So disk ANN aggressively sparsifies the graph. Okay, so it guarantees that the graph and the degrees are small, yet somehow it still performs well. So it's maybe a little bit mysterious how that happens. So Indyk and Chu a couple years ago, tried to bring some theory to this problem. So what they did is they considered a slower version of disk ANN. So this is different. It's not the same algorithm. It's inspired by it. It's quite close. So let me put this S in front of disk ANN to denote that this is the slow preprocessing version. And they argued that this version of disk ANN produces what's called a navigable graph, which I'm going to define formally, but navigable just means you can kind of go from any vertex either directly to another vertex or towards that vertex. Okay. So this version of S-disk ANN doesn't do this aggressive sparsifying. Okay, it does some sparsifying, but it's not as aggressive. And what they showed is that this version of the algorithm in cubic time, they can build a 1 plus epsilon approximate nearest neighbor, and they can do it with log spread n over epsilon to the d space and log squared spread over epsilon to the d log 1 over epsilon query time. Okay, so comparable to these results on the top of the slide. Okay, so again, they're trying to analyze a version of disk ANN to try to say why this algorithm, why would you expect it returns good approximate nearest neighbors. And they also show that this true fast disk ANN, the one that's actually used in practice, that this one has a linear worst case query time, right? So in some sense, they needed to consider this alternative version of it because the true one, well, in the worst case, it's linear time. Now I'll say that in the worst case, it's linear time, but in practice, it works quite well. Okay. All right, so what I want to talk about now is what disk ANN does and the whole idea of how you build a sparse graph. Okay, so I'm going to give a very naive, simple intuition for what you should be looking for. So here I want to build a graph with low space and low query time. So if these are my points, then a very naive first level approximation to this would be to say, build the star graph, right? I pick an arbitrary point, call that my starting point, and then I just add all the edges from this point to every other vertex, right? If I do this, then when a query comes in, I just scan my neighbors and I take the one closest to Q, and lo and behold, I have the exact nearest neighbor, right? But obviously this solution is junk, right? Because this is a linear space solution, so it's sparse in that sense, right? The graph does not have very many edges, but it has linear query time. And remember, linear query time is worthless, right? We can always just scan the points. Okay, so really this is motivating that what we need is not just that the graph is globally sparse, but that it's locally sparse, right? We want low degree along that search path from our start vertex to the destination, right? So we really need to sparsify at all of the vertices, okay? So this is what this S-disk ANN is going to do, okay? It's going to attempt to sparsify for all the vertices, okay? So I'm going to start with the complete graph over P. So I'm not drawing all the edges because that would be a giant mess, but I have initially the complete graph over P. And then I fix some vertex V. So V is my current vertex. I set the neighbors to be everybody else, right? So it's the entire point set other than V. And then I have some parameter alpha. Okay, so alpha is going to be some parameter I can tune. Now what I do is I visit the neighbors in the set N by increasing order of distance from V. So initially I'll visit the first one, but then later it'll just be whatever one is next in the distance ordering. And when I visit this vertex P, so P is the current one I'm looking at, I define this set BVP. So what is this? It's the set of neighbors that are alpha times closer to P than they are to V, right? So this set BVP is the set of things that are alpha times closer to P than they are to V. So what is that geometrically? Geometrically, that's a ball, okay? If you haven't seen this before, this relates to multiplicative Voronoi diagrams. This is known as the Apollonius ball. It's a ball with center P plus 1 over alpha squared minus 1 times the vector P minus V, and radius alpha over alpha squared minus 1, the distance between P and V. Okay, so this is this ball, and it's obviously going to depend, its radius and position depend on alpha. As you increase alpha, what happens is this center drifts more towards P, and the radius of the ball collapses. Okay, good. So this is the set. So what do I do with this set? What I do is I remove the edges from this set. I say V will connect to P, but V will not connect to any other point in this ball. Okay, so this is my sparsification. I am not allowing you to connect to anything else in this ball other than P. So what's happening here is that P is the representative for this ball, right? Approximately, it is, similar distance as everybody else in this ball, right, from V. So so think of P as the representative of this ball. So what I do is I do this at P, then I go to all the neighbors and do this, and then I go to all the vertices in the graph and do this, right? So this is why you get up to this cubic time, okay? So let me remark here what the difference, very high level, what the difference is between the fast disk ANN that's used in practice and this S-disk ANN, which I just described. Okay, I'm not going to go into the full details of fast disk ANN because it's a little complicated and it has some optimizations, but the basic idea is there's sort of two main differences that I'll highlight. First, here, when I visited V, I looked at everybody in the neighbor set. So the neighbor set N started out as all of the point set. In the fast version, they don't do that. They start with some sparse set N. Okay, how they get that, let's not discuss that, but they start with some sparse set already. And then after they run this procedure, they look at every vertex to make sure that that vertex does not have high degree. And if it does have high degree, they just force its degree down. Okay, so they just aggressively thin out the graph. Okay, so that's kind of the difference here, which is why in practice it gets, a very sparse graph. Whereas this S disk ANN may be in low dimensions, it does, but in high dimensions, it may not. Okay, but we're continuing with this S disk ANN to understand how it works. So here's a simple example showing how it sparsifies the graph with respect to V. So here, V is this green vertex. And originally, we started with a point set which was sampled uniformly at random from the square with 200,000 points. Okay. And it's uniformly at random, although we hollowed out a little region around V just so the visualization is nice. But other than that, it's a uniform random sample from the square of 200,000 points. And then what's shown on the right here is all of these Apollonius disks that get created that are used for the thinning. And these blue points are the ones that are left. These are the ones that I'm going to have an edge to, right? So I'm not showing you the original point set. The original point set had 200,000 points. You can see, obviously, this is a significant reduction. And you can also see it kind of is doing what you want it to do in that it is denser near V and it's sparser as you go out, right? Which, because we're, getting a relative approximation, this is the behavior you would want. Okay. So what did Indyk and Chu prove? They proved that this version of disk ANN produces what's known as an alpha navigable graph. So an alpha navigable graph is a graph with the following property. It says that for any two vertices S and T in the graph, either I have the edge from S to T, so I can go directly from S to T, or there is some other vertex y that I can move to such that y's distance to t is a 1 over alpha factor closer, right? So either I can move directly to t or I can move closer to it. And what they showed is that greedy routing, that simple greedy routing on alpha navigable graphs will produce a gamma approximate nearest neighbor, where gamma is related to this alpha parameter here by this ratio alpha plus 1 over alpha minus 1. And then this was later improved in another paper to 1 plus 1 over alpha minus 1. Okay, so there's been a couple papers, looking at this. In our case, we want a 1 plus epsilon approximation. So I'm saying gamma is 1 plus epsilon. That's our goal, which if you take the Indyk and Chu bound and you rewrite it, you get 2 over epsilon plus 1. I think if you take this improved bound, it would be 1 over something like 1 over epsilon plus 1, but doesn't really matter. Okay. So we can now take this expression for alpha and just plug it in for the radius of our Apollonius ball. If I plug it in for the radius and position of my Apollonius ball, I get these two terms. This is where the center is located. This is the radius. Now, these are kind of messy expressions, but what I'm going to do is dramatically simplify them by just saying, look, this has an epsilon squared. I'm viewing epsilon as tiny. So epsilon squared is very small, so I'm going to drop this whole term. And then over here, this is roughly epsilon over 2 times the distance. So I'm saying what this does intuitively is produces an Apollonius ball whose center is near P and whose radius is roughly epsilon times the distance between V and P. So let's look at that picture, right? This was the picture I had before with the Apollonius ball. This is a rather large ball. This is where an alpha, I think, is around 2. Okay? So if what I really should think about here is when epsilon is small, which means alpha is large, this is more what the picture looks like, right? It looks like a small ball whose center is near P and whose radius is a small fraction of the distance between V and P, okay? Good. Okay, so that's S disk A and N, okay? So that's all prior work, right? So what do we do? So as I said, there's some results on graph-based nearest neighbor search that go back to the 90s. I'm sure there are other results I'm just listing to here. There is the Indyk and Chu analysis of this variant of disk ANN, which gets this space and query time. And what we do is two things. First, we sort of think about this disk ANN algorithm and understand it's doing something very close to working on WSPDs. And so we show that actually you can just directly build a graph over WSPDs and you will get the same space and query time. And with a little more work, you can optimize the query time. But our main result is the following. We can construct one of these nearest neighbor search graphs using just greedy permutation. So if you don't know what the greedy permutation is, it's a simple idea, but I'll explain it in later slides. But using this, we can actually get a space that whose bound is independent of the spread and a query time which is still quite good, right? Log spread over epsilon to the d. Okay, so the idea is we're going to give simple algorithms to build these graphs that perform well, right? So our algorithms are going to be simple. They're also going to produce navigable graphs, just like Indic and Chu showed that their graph was navigable. As I said, the WSPD algorithm can be viewed as sort of an interpretable version of disk ANN, and the greedy permutation algorithm is going to remove that log spread factor. Okay, good. Okay. So let me do, by the way, if anyone has questions, feel free to ask. So let me
I have
quickly,
a question, actually.
sure.
In your results, are you thinking about epsilon as like a small constant?
Yes, I'm thinking of epsilon as a small constant, maybe not extremely small, but smallish, yes.
Okay.
Yeah. And again, yeah, so epsilon is small here. Obviously, I have bounds for all of these results, you're getting bounds that are exponential in D. So, D should not be too large either. It's not n to the D, it's epsilon to the D, which is better, but still, this is, the dimension has to be reasonable too. Okay.
Yeah.
Ben,
I
can I
don't know if
ask a
it's
quick question? Oh, sorry, go ahead.
Yeah. Yeah,
yeah,
sorry.
I don't know if it's the correct question to ask. I don't know if it's like in the scope of this talk, but I think do point sets for which they actually construct these graphs in practice, do they suffer from really high dimensionality usually?
In so at least yes, I mean I should say again, it depends what you mean by high dimensionality, right? Like, if we're talking about extremely high dimensions, not necessarily, but 100 dimensions is going to be a problem potentially, right? And 100 dimensions might already be sort of a dimension reduced data set in some sense, right? If that makes sense,
Yeah.
right? So, extremely high dimensions, maybe not necessarily, but even 100 dimensions is problematic. But I
Right.
will say that the spread in some of these data sets is typically quite small. Okay. So that is quite reasonable to assume, especially the log of the spread is small.
Okay, thank you.
Ben, maybe a quick follow-up question is,
Yes.
I think the Indic Ju paper, they talk about like some doubling dimension, which maybe even if the dimension was high, you could believe that that's small even for a high dimensional data set. Are the results you're going to talk about also like would also extend to data sets of low doubling dimension, or is it sort of a different beast?
Yeah, yeah. So everything I say here applies to bounded doubling dimension. There's
Oh, cool.
nothing
Okay.
that we need. There's nothing that we need about it being Euclidean. It's just easier to say it's
Yeah,
Euclidean
yeah,
for
yeah.
me.
Makes sense. Okay,
Yeah.
cool. Thank you.
Okay. Good. So what I want to do quickly then is just tell you about WSPDs if you don't already know what they are, and then just sort of quickly say why disk ANN is doing something like WSPDs, and then I'll jump to our main result, which is this greedy permutation result. So this is just one slide on the background for WSPDs. So just quickly a definition. I'm going to use P cross Q to denote the set of all pairs of points where little p is from capital P and little q is from capital Q. Okay. Then a pair decomposition is this set W, which itself is a set of pairs of sets, right? So I have AI, BI for various values of I, where I have the conditions that AI and BI come from P, AI and BI are disjoint, and this third condition, which is important, that AI cross BI unioned over all I is P cross P, which just says that every pair from the point set is realized in one of these pairs of sets. So every pair appears in one of those pairs. Okay. Then the other definition I need is being separated. So I'm going to say a pair AB, so one of these AI BIs, is 1 over epsilon separated if the maximum of the diameter of A and the diameter of B is at most epsilon times the distance between A and B. Okay, so if I look at this picture here, this is really telling the story. So I have my set A, I have my set B. I've drawn 2 equal radius balls around them. Those balls are the diameter of A, which is larger than B. And so let me call that radius of that ball R. Then I'm saying the separation between the balls is at least R over epsilon, right? So things are far apart between the sets and close within the set. Then W is a 1 over epsilon WSPD if for all I, every AI-BI pair is well epsilon separated, right? So not only are the pairs of points covered, but they're covered in well-separated sets. Moreover, I know that I can compute this decomposition in n log n plus n over epsilon to the d time, and it has size n over epsilon to the d. So again, if epsilon and d are constants, then, I'm getting near linear time construction and linear size. Okay. So good. So that's for WSPDs. Why are these things useful? And it's because they're useful because they're going to give us a representation of all the distances in our point set. So the way to interpret it is as follows. Let me look at this picture again. Look at the set A. I pick an arbitrary point in A. I'm going to call that the representative of A. That's this green and yellow point. I do the same thing in B. I pick an arbitrary point. I call that the representative. And the distance between these representatives is representative of the typical distance between a point in A and a point in B, right? All of the distances between things in A and the things in B are roughly the same as the distance between these representatives, which means I can just compute representatives for everybody or just select representatives for everybody. And then the distances between those representatives are approximately capturing all the distances in my point set. Okay, so it's a compact representation of my distances. So if I then go back and look at disk A and N, this variant that was considered by Indyk and Chu, and I look at this Apollonius ball around P, what did we say? We said its center is near P, so it's roughly at P, and its radius is, roughly epsilon times the distance between V and P. So what is this actually saying in the language of WSPDs? It's saying the point V against this red ball around P, well, they're well-separated sets. That's what it's saying. It's saying V is well separated from the red ball, which means that when I earlier deleted the edges from V to everything in the ball except for P, what I did is just say P is the representative in that well-separated pair, and I just connected to the representative. And in fact, this is what we can show. We can show that if you construct a WSPD, you can directly build a good graph, right? So I construct the WSPD, which is a standard thing to do, right? I construct an 8 over epsilon WSPD, and then for every pair from the WSPD and for every set in that pair, I create a representative rho X. And then what I do is I add these edges. I say for the pair AB, I add edges from everything in B to the representative in A, and I add edges from everything in A to the representative in B. And then I just union these things together. I'm not going to cover it here, but it's known that every point appears in only epsilon to the minus d log spread pairs. And so the total number of edges that I created is just n times that. It's just going to be n times epsilon to the minus d times this log spread term. Okay, so that's the size of the graph. That was the bound that I wanted to get from the previous slides. And you can argue that if I do greedy routing on this graph, you get a 1 plus epsilon approximate nearest neighbor, and you get it in query time log spread over epsilon to the d log 1 over epsilon. This is the query time that the disk A and N analysis got. And in fact, we show in the paper you can improve this. Okay, but if you just do sort of the direct analysis, you'll get the same bounds using a WSPD as this disk ANN, this S-disk ANN algorithm got. Okay. Now, I could show you the details of this analysis. I have a slide, but I think it's rather dry, and I'd rather get to the main results. So let me skip this analysis, and let me jump straight to the main result. So the main result of the paper is not the WSPD result, it's this greedy permutation result. So this is going to be a simple approximate nearest neighbor graph that I build using just basic things from greedy permutations. So what is a greedy permutation? So first, let me consider an ordering P1 through Pn of P. So some permutation of the points. And let me look at the ith prefix Pi. So capital P sub I is the first I points. Okay. Then I'm going to call P1 through Pn a greedy permutation if it satisfies this property. First, P1 is an arbitrary point, so that's not much of a requirement, but P1 is an arbitrary point. And then for all other I, Pi is the point in P furthest away from the I-1 prefix, right? So I'm building up this ordering, and I always take the next point as the furthest point from the things I've already selected. Okay, this defines a set of radii where Ri is the distance to the prefix Pi, right? So I have my current prefix Pi. Ri is the distance of the furthest point. So actually Pi plus 1 will be added at distance Ri. And it's not too hard to see that these Ri's are going to be a decreasing sequence because as I add more points, I'm better covering things. So let me actually show you what this looks like with a picture. Okay, so I have my point set. I pick an arbitrary point. This is P1. Then I pick the point furthest away from that. That's P2. That's over here. Then I pick the point furthest away from these 2 points. That's this third point. Then I pick the point furthest away from those. That's this fourth point. The furthest from those 4 is this point. Okay, so I can keep going and I can build up the whole permutation. Okay, so if you're familiar with k-center clustering, this is essentially the 2 approximation algorithm for k-center clustering. So good, so I build up this permutation this way, and just if you want to visualize it, this is what is going on, right? So if I look at the 4 red points that I've added, so that's the 4, this is the prefix for the first 4, then P5, the 5th point, will be the furthest point from that, and it will be at a distance of R4. Okay, so just remember this difference, this off by 1 between the radius and the point. So, but I can also observe here some nice things. If I look at these balls of radius 4 around these 4 points, first, they cover everybody, right? Every one of the black points is in one of these balls. And moreover, the distance between the red points is at least R4, meaning any one of these balls does not contain a center of another ball, right? So they cover, they produce a net, a nice, well spread out coverage of the point set. Okay, good. So for this for this greedy permutation, it's known that in n log n time, you can compute an approximation to it, okay? The exact one, for our purposes, let's just think about this as the exact result, but technically if you want this time, it's an approximation. But remember always there's a trivial quadratic time algorithm to compute this thing. You can do better than that, but there's a trivial quadratic time algorithm. So it's not a hard thing to compute. And it produces an RI packing. So this is what I was just talking about on the previous slide. So for every point in the point set, it's going to be a distance at most RI from the prefix PI. And for any 2 points in PI, their distance is at least RI apart, right? Again, I'm saying everything is covered by one of these balls at radius R4, and the points in the red points are all distance at least R4 apart from each other, right? So this is what I mean by a packing. The last thing I need to define is this notion of friends list. Okay, so if I have a point pi, I'm going to define its friends as the set of things from the prefix, I minus 1 prefix, which are in a ball around me at radius 8 ri minus 1 over epsilon. Remember, pi is added at radius r minus 1. So this is a slightly expanded ball. So these are points that are sort of relatively close to pi relative to the distance it was added. And these friend lists can also be computed too easily, or efficiently, I should say. Okay, so here's my point set. Now here, I'm not showing you the entire point set. I'm only showing you the prefix. This is the ith prefix, okay? Now pi, when it is inserted, it's inserted at some distance ri minus 1 from the prefix points. So what I'm saying is I enlarge that ball by a factor of 8 over epsilon, and then everybody in that ball is my friend. Okay, so this is the friend list. And I can make two easy observations. First, if you're my friend, if PJ is in the friend list of I, then J is less than I. But that's obvious because I only added edges from prefix. I only said things are friends if they're in my prefix. So obviously they have to have smaller index. The other observation is that the number of friends is bounded because pi minus 1, which are these black points, that is an ri minus 1 packing, right? That's what we set up here, which means if I look at this 8 ri minus 1 over epsilon ball, I'm saying everybody in this ball that are friends of me, their distance between each other is at least ri minus 1. So now what I'm trying to do is pack, which would tell me that ri minus 1 over 2 balls around each one of those are disjoint. So now I'm packing interior disjoint balls into a larger ball, and I get this ratio, 8 ri minus 1 over epsilon divided by r minus 1 over 2, right? And if I raise that to the d power, that's roughly the number of balls that you can pack, which is 1 over epsilon to the d. So here, by the way, there was this question about whether our analysis works more generally in bounded doubling dimensions, and the answer is yes. This is basically, I'm saying here, this is the doubling dimension showing up, right? So we're visualizing it as Euclidean, but really it just works immediately for bounded doubling dimension. Okay, good. So the number of your friends is bounded. So now what's the graph construction? I mean, basically, I've already told you intuitively what it should be. So it's very simple. I give you the point set and epsilon as the input, and then I'm going to compute a greedy permutation, and then my edge set is just going to be the friends, right? So for every I look at the friends of I, and I add an edge from that friend to pi, and that's it. That's the graph, okay? And obviously this friend, what's in the friends list depends on this parameter epsilon, okay? And then I'm going to store the edges for a given vertex in a certain order, right? So I have edges leaving this vertex. I'm going to store them in increasing index order. Okay, so when I look at my neighbors, I always look at them in terms of increasing index. Okay. So then how do I answer a query? It's very simple. I start at P1. So C is my current point. I start at P1. I scan the outgoing edges of my current point C. And again, I've ordered them in increasing index, so I'm scanning them in increasing index. And then the first time I see a point Pj, which is 1 minus epsilon over 4 closer than I currently am, then I just move to that point. Okay, so I just greedily move, as I mentioned earlier. And then I just keep doing this until I get stuck, right? At some point I get stuck, I can't advance, and that's it, right? So this is, again, this is the impulsive greedy algorithm, right? This is the simplest sort of algorithm you could do on these graphs. Okay. So what I want to show is the following theorem, that for endpoints in a parameter epsilon, this graph, the one I just described, has n over epsilon to the d edges, and given a query, it gives me a 1 plus epsilon approximate nearest neighbor, and it does so in log squared spread over epsilon to the d plus 1 time. Okay? Now, the number of edges is easy to bound because I already told you that for all I, the friends are bounded by 1 over epsilon to the d. So then the total number of edges is just n times that. Okay, so immediately we get that this graph has good space. Okay. What I need to argue now is that it's both a 1 plus epsilon approximate nearest neighbor and that it has good time, okay, for the query. So let me argue the time bound first. And as I said, this time bound can be improved, but I'll just argue this version of it. So if I want to bound the query time, I can do the following sort of trick. I can bin distances by their scale. Okay, so here's L. L is some value, some distance. I'm going to call the edge Pj to Pi L admissible if Pj to Pi is in the range L over 2 to L, right? So it's roughly L, within a factor of 2. Well, if it's L admissible, then the distance is at least L over 2. But if this edge exists by definition of friends, then I have this upper bound on the distance, which if you just bring that epsilon to the other side, this is telling me that this Ri minus 1 is at least epsilon L. Now, why do I care about that? Because this is, again, giving me a packing condition, right? So the graph looks, the figure looks like this. I have Pj. I'm looking at the scale L. So I'm looking between L over 2 and L. So these are the things that I care about. And I'm saying if I have an edge to that point, then if I look at any pair that I have an edge to, their distance is at least epsilon L. So again, this is this standard packing argument. I have an L radius ball. I have things that are epsilon L apart. So I get 1 over epsilon to the d as the number of outgoing edges at scale L, right? So if that's the number at scale L, now I can just sum up over all the scales, right? So I say n of PL is the number of L admissible edges. So then the total number of edges would just be the sum over this quantity, the diameter over 2 to the I, from I equals 0 to the log of the spread, right? So I keep doubling. Those are my bins. And then I just get log spread over epsilon to the d. Okay, so this is a bound on the out degree of any vertex. Now, how many steps does the algorithm perform? Remember, every time I take a step, I promise you that the distance goes down by 1 minus epsilon over 4, right? That was my condition for moving, which means that the log of 1 over 1 minus epsilon over 4 of the spread is the number of times I can do this before I actually hit my goal, right? So that's roughly log spread over epsilon. So this is the total number of times I can move. And I just told you the cost of a move is log spread over epsilon to the d because the cost of the move, in the worst case, I scan all of my neighbors before I move, right? So it's the cost per move times the number of moves, and this gives me this log squared over epsilon to the d plus 1 bound, okay? So that bounds my query time.
Ben, can I ask a naive question?
Yes, sure.
Like you differentiated between sort of like this opportunistic greedy where you like move as soon as you find an improvement and like the other version where I guess you take the best of your neighbors. I guess like this you're saying this bound would also hold if you did the greedy, right? Where
Yes, it would hold if I did. You're saying the stronger version of greedy where I move to
yeah.
a neighbor. Yeah, but with the
Yeah.
condition that I make progress. Right. I want to make sure that I make sufficient progress.
But your graph promises that, or there's always an edge that makes progress.
There is always an edge that makes progress, but I think if you don't, I have to think about it. You may need also this condition that you locally make progress so that you know that you need to know when you hit the nearest neighbor.
Ah,
Right? You could sort of get very close to it and already be at the goal in some sense and not know. I think naively you may need this, but maybe it's okay. I have to think about it.
okay. Okay.
Yeah.
Okay, thanks.
Okay, good. So how much time do I have? What time is it now? So,
It's 52.
okay, so if I go over the correctness, it probably takes me 5 to 10 minutes. So do people, should
Yeah,
I go
I think
over?
that's fine. I think that's
Okay.
fine.
Okay, so this is so I have two things to do. I show this and then I have some plots, although the plots are some good and bad news. So, okay, so let me go over the approximation bound. Okay, so I want to argue that this thing produces a 1 plus epsilon a and n. Okay, so let pj be the point that I'm currently at, right? I'm walking in my graph. I'm currently at pj, and let capital L be the distance to the query, and let little l be the distance of the nearest neighbor to the query, right? So I'm at capital L distance, but I'd rather be at little l distance, right? Now, if capital L is less than or equal to 1 plus epsilon L, I will get the desired a and n, right? So I will succeed in that case. So let me suppose that L is too large. Capital L is more than 1 plus epsilon little l. Well, in this case, you get this kind of messy expression, but don't worry too much about it right now. Just look at these terms. 1 minus epsilon over 4 capital L minus epsilon over 4 capital L. Through some very basic algebra, I can show that this is going to be strictly greater than little l. Okay, now why do I care about showing that? Because of the following picture. So let's look at this picture. So here I have Q, my query point. Capital L is the distance to Pj, my current position. T is the true nearest neighbor. And now I can start interpreting these values. So epsilon over 4L, that's going to be this psi value. That's going to be this ball that I place around the true nearest neighbor. Okay? So I have this ball around the true nearest neighbor. And then I have this bigger ball, capital B, which is I start with the ball from Q to Pj, and I shrink it by 1 minus epsilon over 4. And what this inequality up here says is it says that the distance from Q to T, that's L, plus epsilon over 4 capital L, that's the radius of the green ball, that is strictly less than 1 minus epsilon over 4 capital L. That's the ball capital B. So I'm saying that capital B completely contains this little green ball around the true query, the true nearest neighbor. Okay. So why do I care about this ball capital B? Well, capital B is a 1 minus epsilon over 4 scaling down of the distance from Q to J, which means what? It means that I cannot have scanned a point inside this ball. Because if I had scanned a point inside this ball, I would be at that point or something closer, and I wouldn't be at PJ. Okay, so that's why I'm looking at this ball. And now what I can do is consider P alpha. So what is P alpha? P alpha is the smallest index point that lies in the green ball. So it's the smallest index point in the green ball. I can do a simple calculation here. R alpha minus 1, we know that's at least R alpha. R alpha, by definition, is the distance from P alpha to P alpha minus 1. P alpha is, again, by construction, the furthest point from the prefix, which means it's at least as far as T from the prefix. And this quantity right here is at least psi, the radius of the green ball. Why is this greater than psi? Because alpha is the smallest index point that hits that green ball. So if it wasn't, then that would mean that would contradict P alpha being the first index point that hit it. Okay, so good. So summary, I have R alpha minus 1 is greater than or equal to psi, which lets me conclude the key fact. The key fact is that Pj minus P alpha, so again, here's Pj on the outside here, P alpha is a point in this green ball. I can conclude by triangle inequality that this thing is less than or equal to 8 over epsilon R alpha minus 1. If you want to see what happens here, I just take the triangle inequality, I expand it into these three terms. pj minus q, that is exactly capital L, and qt and t to p alpha, that's q to t and t to something in this ball, which is going to be inside the bigger one. So that these two terms are also less than L, so together they're less than 2L. And 2L, well, there's an exact expression in terms of L relating L and psi, and I just argued that psi is less than R alpha minus 1. Okay? So I did that maybe kind of fast, but the main point is that the distance from Pj to P alpha is less than or equal to 8 over epsilon R alpha minus 1, which is key because that is the condition for it being a friend. Right? So what I'm saying, so let me assume that alpha is greater than j. In a second, I'll say that it actually has to be, but just assume that now. If alpha is greater than j, and pj to p alpha is less than or equal to 8 over epsilon R alpha minus 1, that means pj by definition is a friend of alpha. So the edge pj to p alpha is there.
Screen reader called VoiceOver. If you know how to use VoiceOver, press
sorry.
Command F5 now to.
No problem. Right. So my conclusion is that pj has an edge to this point p alpha that's in that ball. Now, the distance from q to p alpha, that is at most the distance from q to t and t to p alpha by the triangle inequality. Q to t, that's little l, this little l value, the true nearest neighbor distance. And t to p alpha, well, because p alpha is in that ball, it has distance at most epsilon over 4L. And now because L is greater, capital L is greater than little l, you can argue that this is at most 1 minus epsilon over 4 capital L. So what's the summary here? I'm saying that the distance from Q to P alpha is less than or equal to 1 minus epsilon over 4L, which is my condition to move there. And I've told you the edge Pj to P alpha exists, which means that the algorithm is going to move to P alpha from Pj, or at least something that's at least a 1 minus epsilon over 4 factor closer, right? So this basically says I'm going to succeed, okay? And then you can argue actually that, so this was assuming alpha is greater than j. It's not too hard to argue that actually alpha has to be less than or equal to j. Maybe let me skip that and let me go, because I'm kind of running low on time. Let me go to the last slide. Okay, so this is the analysis. I've argued successfully that you are going to always make improvement, which means I'm going to end up with a 1 plus epsilon approximation. We already bounded the number of steps, right? That was a previous analysis. Okay, so what's the summary? The summary is that this version of disk ANN by Indick and Chu had this space and query time. With WSBDs, you can basically get the same space and query time. You can improve the query time a little bit if you want. And with this simple greedy permutation idea, you can actually get a space bound that is independent of the spread and still good query time, right? Log spread over epsilon to the d. Okay, the last thing that I want to show is these plots. So these plots, so Sariel sent me these plots over the weekend, and I'll say these plots show some good news and some bad news, okay? But nothing unexpected, okay? So what do we have here? So I have a real nearest neighbor data set with 30,000 points and dimension d equals 128. Okay, so this is this, not crazy high dimension that I was saying, but still high if you have an epsilon to the d factor, which both R's and this S disk ANN have, right? So in these plots, you can kind of think of S disk ANN as kind of maybe similar to R results, okay? Now, what you see on the plots here, on the y-axis is the success rate. So the y-axis is showing how many times, what fraction of the queries do I get the real nearest neighbor? This is not approximate nearest neighbor. This is how often do I get the true nearest neighbor in the data set. And what you see on the x-axis is the width. Remember, for this greedy search algorithm, I said you could also use a queue that would be a little less greedy. That's what this is. The width is the queue size. So the greedy version that we've been talking about most of the lecture, that would be when the width is 1. Okay, that would be all the way at the left. That's the axis, the y-axis here. Okay, and you can see even in the greedy regime, So that's the y-axis. You can see these are different values of our greedy algorithm for different values of epsilon. You can see that when epsilon is small, we are getting the nearest neighbor almost all of the time, right? This is a real data set. We are getting the true nearest neighbor almost all of the time. And now I can look at disk ANN. So disk ANN here in these plots, this is not the slow disk ANN index by, sorry, it's not the slow disk ANN looked at by indic and true. This is the true disk ANN, the optimized one that enforces sparsity and is used in practice. That true disk ANN one, it's probably hard to see, but it's sort of this sixth curve down. It starts off at maybe about 30%, but then it jumps up as I increase the width. Okay? So, at least in the regime for the parameter tuning that is used by default for disk ANN, the real disk ANN, it doesn't start out as a navigable graph, right? Being high on this axis means I'm navigable. Lower means I'm less navigable. So it's not starting out navigable, but if they increase the queue size, they do quickly jump up. Okay? Now, I'm not saying this is a fair comparison because, you could set the parameters different on disk ANN, but at least with their default settings, this is what's going on. Okay, so we're navigable, and that's good news. What's the bad news? The bad news is pretty bad, but maybe to be expected. Let's look at the average cost, right? So this is how many distance evaluations we do. This is an exponential scale here. If you look at our algorithm with greedy at, epsilon at 0.2, this value is basically saying I'm looking at everybody in the graph. Okay? So now if you increase epsilon, you can get better performance, right? At 10 to the fourth, you're maybe looking at a third of the graph, and then down here, you're doing significantly better. Okay? But let's look at what disk ANN is doing. Disk ANN is starting off way here at the bottom, right? Now, that's not just by magic. That's because disk ANN enforces that the degrees are low. It's a hard requirement for them, right? And as you can see, as the width increases, it increases. There's some regimes where we beat it, but those are with larger values of epsilon. So this is all to be expected because remember here, the dimension is 128. Our bounds are essentially horrible for this dimension, right? They're exponential in the dimension. The mystery is, so we're getting these bounds. We're showing that with the way disk ANN sets its parameters by default, it's not navigable, at least not with those parameters. But if you increase the width, it still gets good success rate. Yet somehow it's able to do this with a very sparse graph. So I think what these results are showing is that, we're getting a navigable graph. That's great. But there's still some maybe disconnect between what's really going on with disk ANN. Why is it performing well in practice? It's maybe not because it's producing a navigable graph. There may be something else going on there, right? So I think this is saying that the theory and practice aren't really matching yet.